After studying this module, you shall be able to know about the tests that are used to check the stationarity and co-integration in panel data. Researchers often cross-country over time data to study purchasing power parity, international R&D spillovers, and the growth convergence. Nowadays, the focus of panel data econometrics has shifted towards studying the asymptotics of macro panels with large N, that is number of countries cross sections, and large T, that is length of time series, rather than using asymptotics of shorter panels with large N and small t. The limiting distribution of double indexed integrated processes has been studied extensively by Phillips and Moon in 1999 and 2000. The fact that t is allowed to increase to infinity in macro panel data generated two strands of ideas in which the first idea rejected the homogeneous behavior of the regression parameters, implicit in the use of pooled regression in favor of heterogeneous regressions, that is, one for each country. There are some literatures that critically rely on t being large to estimate each country's regression separately and further warn against the use of standard pool estimators such as fixed effect to estimate dynamic panel model data, arguing that they are subject to large potential bias when the parameters are heterogeneous across countries and regressors are serially correlated. Some of the distinctive results that are obtained with non-stationary panel data are that many test statistics and estimators of interest have normal limiting distributions. That is, in contrast to non-stationary time series literature where the limiting distributions are complicated functionals of Wiener processes. Unit root tests for panel data. Before proceeding to unit root tests, let us recall that the concept of non-stationarity in case of time series, a non-stationary series has time-dependent mean or variance. In other words, there is no long-run mean to which the series return. The variance is time-dependent, and as time approaches to infinity, it also goes to infinity. Theoretical autocorrelations do not decay, but in finite samples, the sample correlogram dies out slowly. Testing for unit roots in time series is a common practice among researchers and is considered to have an important place in econometrics courses. 1. Levin, Lin and Chu test, LLC. Levin, Lin and Chu test argued that the power of individual unit root test is limited against alternative hypotheses with highly persistent deviations from equilibrium. This is particularly served in small samples. LLC suggests a more powerful test for unit root testing than performing individual unit root for each cross section. The null hypothesis states that each individual time series contain a unit root, that is, it is non-stationary series, whereas the alternative hypothesis states that each time series is stationary, that is, non-stationary series. This can be written as change in yit is equal to rho yit minus 1 plus summation L going from 1 to pi theta il change in yit minus L plus alpha mi dmt plus epsilon it. M is equal to 1, 2, 3, where dmt indicating the vector of deterministic variables and alpha mi the corresponding vector of coefficients for model M is equal to 1, 2, 3. More precisely, d1t is equal to empty set, d2t is equal to 1 and d3t is equal to 1t. Since the lag order pi is unknown, LLC suggests a three-step procedure to implement the test. Step 1. Perform separate augmented decufuller regressions for each cross section. Change in yit is equal to rho I yi t minus 1 plus sigma L going from 1 to pi theta il change in yit minus L plus alpha mi dmt plus epsilon it. M is equal to 1, 2, 3. The lag order pi is permitted to vary across individuals. For a given t, choose a maximum lag order Pmax and then use the t statistics of theta small l capital L hat to determine if a smaller lag is preferred. These t statistics are distributed normally with 0 mean and 1 variance under the null theta il is equal to 0. both when pi is equal to 0 and when pi is less than 0. Once pi, the lag order, is determined, two auxiliary regressions are run to get orthogonalized residuals. Run change in yit on change in yit minus L is equal to 1 going till pi, and dmt to get residuals eit hat. Run yit minus 1 on change in yit minus L from 1 to pi, and dmt to get residuals vit minus 1 hat. Standardize these residuals to control for different variance across I. eit tilde is equal to eit hat divided by sigma epsilon L hat, and vit minus 1 tilde is equal to vit hat divided by sigma epsilon L hat, where sigma epsilon L hat is equal to standard error from each augmented Dickey-Fuller regression for I is equal to 1 to n. Step 2. Estimate the ratio of long run to short run standard deviations. Under the null of a unit root, the long run variance of equation 1 can be estimated as sigma yl hat square is equal to 1 divided by capital T minus 1 summation small t going to t from t to capital T change in yit square plus 2 summation capital L from 1 to k bar w k bar L brackets 1 divided by t minus 1 summation small t is equal to 2 plus L to capital T change in yit into change in yit minus L brackets closed, where k bar is a truncation lag that can be data dependent. K bar must be obtained in a manner that ensures the consistency of sigma yit hat square. For a Bartlett kernel, w k bar L is equal to 1 minus brackets L divided by k bar plus 1 brackets closed. Step 3. Compute the panel test statistics. Run the pooled regression. eit tilde is equal to rho vit minus 1 tilde plus epsilon it tilde based on n t tilde observations, where t tilde is equal to t minus p bar minus 1 is the average number of observations per individual in the panel, with p bar is equal to summation I from 1 to n pi divided by n is the average lag order of individual augmented Dickey-Fuller regression. LLCs suggest that their test can be used for panels of moderate size with n between 10 and 250 and t between 25 to 250. The limitations of this test are: A. It crucially depends upon the assumption of independence across cross-sections. B. It is also not applicable if there exists cross-sectional correlation and the assumption that all cross-sections have or do not have unit root is restrictive. 2. Pesaran and Shin test (IPS). Unlike LLC, IPS test allows for a heterogeneous coefficient of yit minus 1 and propose an alternative testing procedure that is based on average of individual unit root statistics. That is, IPS suggests an average of the ADF test when error term mu it is serially correlated with different serial correlation properties across cross-sectional units. That is, from 1, null hypothesis minus pi is equal to 0 for all I, and the alternative hypothesis allows for some, not all, of the individual series to have unit roots. That is, alternative hypothesis pi less than 0 for I is equal to 1, 2, 3 going till n1, and pi is equal to 0 for I is equal to n1 plus 1 going till n. 2. Formally, it requires the fractions of the individual time series that are stationary to be non-zero. That is, limit n tends to infinity, n1 by n is equal to delta, where 0 is less than delta less than 1. This condition is necessary for the consistency of the panel unit root test. The IPS T-bar statistics is written as the average of the individual ADF statistics as T-bar is equal to 1 upon n summation I from 1 to n TPI, where TPI is the individual T statistics for testing H0, that is Pi is equal to 0 for all I, in 2 when the lag order is always 0, that is Pi is equal to 0 for all I. IPS provides simulated critical value for T-bar for different number of n cross sections, T, series length and decay-Fuller regressions containing intercepts only or intercepts and linear trends. In general case, when the lag order Pi may be non-zero for some cross sections, IPS show that a properly standardized T-bar asymptotic normal distribution. Third, Breitung's test. Both LLC and IPS tests require n, that is cross sections, to be small enough relative to T. This is because both tests may not keep nominal size well when either cross sections is small or n is large relative to T. Breitung in 2000 studies the local power of Levin, Lin and Chu test and IPS test statistics against a sequence of local alternatives. Breitung finds that both these tests suffer from dramatic loss of power if individual specific trends are included. The reason for this is the bias correction. Under the sequence of local alternatives, the bias correction also removes the mean, so he suggests a test statistic without a bias adjustment. The power of this test statistic is substantially higher than LLC or the IPS test while using Monte Carlo experiments. Breitung's test statistics without bias adjustment is obtained as follows. Step 1. Same as LLC, perform the separate augmented decay-Fuller regressions for each cross section. Change in YIT is equal to rho I, YIT minus 1 plus summation L going from 1 to Pi, theta IL, change in YIT minus L plus alpha MI DMT plus epsilon IT, M is equal to 1, 2, 3. The lag order Pi is permitted to vary across individuals. For a given T, choose a maximum lag order Pmax and then use the T statistics of theta small l capital L hat to determine if a smaller lag is preferred. These T statistics are distributed normally with mean 0 and variance 1 under the null theta IL is equal to 0, both when Pi is equal to 0, when Pi is less than 0. Once Pi is determined, two auxiliary regressions are run to get orthogonalized residuals. In this test only, change in Yi T minus L is used in obtaining the residuals EIT hat, Vi T minus 1 hat. The residuals are then adjusted to correct individual specific variances. Step 2. The residuals are transformed using the forward orthogonalization transformation employed by Arellano and Bova. EIT star is equal to under root T minus small t divided by T minus small t plus 1 brackets EIT tilde minus EI tilde comma T plus 1 plus EI tilde comma T divided by T minus small t bracket closed. Also with intercept and trend, Vi star comma T minus 1 is equal to V tilde I comma T minus 1 minus Vi tilde comma 1 minus T minus 1 divided by capital T V tilde IT. With intercept and no trend, the equation is Vi star comma T minus 1 is equal to Vi tilde comma T minus 1 minus Vi comma 1 tilde. With no intercept and trend, Vi star T minus 1 is equal to Vi comma T minus 1 tilde. Step 3. Run pooled regression. EIT star is equal to rho Vi star comma t minus 1 plus EIT star, and obtain the t statistic for null hypothesis rho equal to 0, which has in the limit a standard distribution with 0 mean and 1 variance. 4. Combining the p-value test. Let GITI be a unit root test statistic for ith group in 1, and assume that as the time series observation for the ith group Ti tends to infinity, GITI is equivalent to Gi, where Gi is a non-degenerate random variable. Let Pi be the asymptotic p-value of a unit root test for cross-section I, that is, Pi is equal to GITI, where the function is the distribution function of the random variable Gi. Madala and Wu and Choi proposed a Fisher-type test. P is equal to minus 2 summation I from 1 to n log Pi. It combines the p-values from unit root test for each cross-section I to test for unit root in panel data. Note that minus 2 log Pi has a chi-square distribution with 2 degrees of freedom. This means that P is distributed as chi-square with 2n degrees of freedom as Ti tends to infinity for finite n. Both IPS and Fisher test are different from LLC in a way that they relax the assumption of LLC test that rho I is the same order under the alternative. Both the IPS and Fisher tests merge the information based on individual unit root test. However, the Fisher test has the advantage over the IPS test in that it does not require a balanced panel. Also, the Fisher test can use different lag lengths in the individual ADF regression and can be applied to any other unit root test. The disadvantage is that the p-values have to be derived by Monte Carlo simulations. Madala and Wu in 1999 find that the Fisher test performs the best when bootstrap-based critical values are used and is preferred choice for testing non-stationary as the null and also in testing for cointegration in panel. Choi in 2001 applied the combining p-value test and the IPS test to panel data of monthly US real exchange rates sampled from March 1973 to March 1996. The combining p-value tests provided evidence in favor of the PPP hypothesis, while IPS didn't. Fifth, residual-based LM test. Hadri in 2000 derives a residual-based Lagrange multiplier test where the null hypothesis is there is no unit root in any of the series in the panel against the alternative of a unit root in the panel. This is a generalization of KPSS test from time series to panel data. It is based on ordinary least squares residuals of YIT on a constant or on a constant and a trend. In particular, Hadri considers the following two models. YIT is equal to RIT plus epsilon IT. YIT is equal to RIT plus beta IT plus epsilon IT. I going from 1 to n and t going from 1 to t, where RIT is equal to Ri comma t minus 1 plus mu IT is a random walk. Epsilon IT is distributed IIN with 0 mean and standard deviation sigma square epsilon, and mu IT is distributed IIN with sigma square mu. Are mutually independent normal that are IID across I and over T. Using back substitution, model 4 becomes YIT is equal to Ri naught plus beta IT plus summation S going from 1 to T mu IS plus epsilon IT gets reduced to Ri naught plus beta IT plus VIT, where VIT is equal to summation S going from 1 to T mu IS plus epsilon IT. The stationarity hypothesis is simply the null hypothesis that sigma mu square is equal to 0, in which case VIT is equal to epsilon IT. The LM statistics is given by LM1 is equal to 1 upon n ratio of summation I going from 1 to n 1 by t square summation t is equal to 1 by t SIT square divided by sigma square epsilon hat, where SIT is equal to summation S from 1 to t epsilon LS hat are the partial sum of OLS residuals epsilon LS hat from YIT is equal to RI naught plus beta IT plus summation S from 1 to t mu IS plus epsilon IT is equal to Ri naught plus beta IT plus VIT. And sigma epsilon square hat is a consistent estimate of sigma square E under the null hypothesis H naught. A possible candidate is sigma epsilon hat square is equal to 1 upon nt summation I going from 1 to n summation t going from 1 to t epsilon IT hat square. Hadri in 2000 suggested an alternative LM test that allows for heteroscedasticity across I, say sigma square EI, sigma square epsilon I. LM2 is equal to 1 upon n brackets summation I from 1 to n brackets 1 upon t square summation small t going from 1 to capital T SIT square divided by sigma epsilon I hat square, both the brackets closed. Fourth, test for cointegration. Like panel unit root tests, panel cointegration tests can be motivated by the search for more powerful tests than those obtained by applying individual time series cointegration tests. The latter tests are known to have low power, especially for short t and short span of the data, which is often limited to post-war annual data. 1. Cow test, also known as residual-based decuphyller and augmented decuphyller test. Consider the panel regression model YIT is equal to X dash IT beta plus Z dash IT gamma plus EIT, where YIT and XIT are I1 and non-cointegrated. For ZIT is equal to mu I. Cow proposed decuphyller and augmented decuphyller type unit root test for EIT as a test for null of no cointegration. The decuphyller type test can be calculated from the fixed effect residuals. EIT hat is equal to rho EIT minus 1 hat plus VIT, where EIT hat is equal to YIT tilde minus XIT tilde beta hat and YIT tilde is equal to YIT minus YI bar. In order to test the null hypothesis of no cointegration, the null can be written as H naught, that is rho equal to 1. The OLS estimate of rho and the t statistics are given as rho hat is equal to summation I going from 1 to n, summation t going 2 to capital T, EIT hat EIT minus 1 hat divided by summation I from 1 to capital N summation t from 2 to capital T EIT hat square. T rho is equal to rho hat minus 1 into under root summation I is equal to 1 to n summation t is equal to 2 to t EIT minus 1 hat square divided by SE, where SE square is equal to 1 upon nt summation I from 1 to n summation t from 2 to capital T into EIT hat minus rho hat into EIT minus 1 hat whole square. Cow proposed following decuphyller type test. Decuphyller rho is equal to root n into capital T brackets rho hat minus 1 plus 3 root n divided by root 10.2. Decuphyller test T is equal to root 1.25 T rho plus 1.875 n under root. Decuphyller rho star is equal to root n into capital T into rho hat minus 1 plus 3 root n sigma hat v square divided by sigma hat ov square divided by under root 3 plus 36 sigma hat v4 divided by 5 sigma hat ov to the power 4. Decupula T star is equal to T rho plus root 6n sigma hat v divided by under root sigma hat ov square divided by 2 sigma hat v square plus 3 sigma hat v square divided by 10 sigma hat ov square, where sigma hat v square is equal to summation hat yy minus summation yx hat into summation xs hat to the power minus 1. Sigma hat ov square is equal to omega hat yy minus omega hat yx into omega hat xx to the power minus 1. Summation omega is equal to variance long run matrix. While df rho and dft are based on the strong exogeneity of the regressors and errors, df rho star and dft star are the co-integration with endogenous relationship between regressors and errors. For ADF test, we can run the following regression. EIT hat is equal to rho EIT minus 1 hat plus sigma j from 1 to p Vj change in EIT minus j hat plus VITP with the null hypothesis of no co-integration. The ADF test statistics can be written as ADF is equal to T ADF plus root 6n sigma hat v divided by under root sigma hat square ov divided by 2 sigma hat square v plus 3 sigma v hat square divided by 10 sigma ov hat square, where TADF is the test statistics of rho in EIT hat is equal to rho EIT minus 1 hat plus summation j is equal to 1 to p Vj change in EIT minus j hat plus VITP. 2. Residual based LM test. This test is derived by Pekoksky and Cow in 1998. It is used to test the null of co-integration rather than the null of no co-integration in panels. This test is an extension of the LM test and the locally best invariant test for an MA unit root in the time series literature. Under the null, the asymptotic no longer depend on the asymptotic properties of the estimating spurious regression. Rather, the asymptotic of the estimation of a co-integrated relationship are needed. For models which allow the co-integrating vector to change across the cross-sectional observations, the asymptotic depend merely on the time series results as each cross-section is estimated independently. For model with common slopes, the estimation is done jointly and therefore the asymptotic theory is based on the joint estimation of a co-integrated relationship in panel data. For the residual based test of the null of co-integration, it is necessary to use an efficient estimation technique of co-integrated variables. In the time series literature, a variety of methods have been shown to be efficient asymptotically. These include the fully modified OLS estimator of Phillips and Hansen and the dynamic least squares estimator proposed by Saikonen and Stock and Watson in 1993. For panel data, Cow and Chiang showed that both the FM and OLS methods can produce estimators which are asymptotically normally distributed with zero means. The model presented allows for varying slopes and intercepts. YIT is equal to alpha I plus x dash IT beta I plus EIT. XIT is equal to XIT minus 1 plus epsilon IT. EIT is equal to gamma IT plus mu IT, and gamma IT is equal to gamma IT minus 1 plus theta mu IT, where mu IT are IID with zero mean and sigma square mu standard deviation. The null hypothesis of co-integration is equivalent to theta is equal to 0. The test statistic proposed by Pekoksky and Cow is defined as LM is equal to 1 divided by n, summation I is equal to 1 to n, 1 by t square, summation t is equal to 1 to capital T, SIT square, divided by sigma E hat square, where SIT is a trial sum process of the residuals. SIT is a trial sum process of the residuals. SIT is equal to summation j from 1 to t, Eij hat, and sigma square E hat is defined in Minkowski and Cow. Third, Pedroni test. Pedroni proposed several tests for the null hypothesis of cointegration in a panel data model that allows for considerable heterogeneity. His tests can be divided into two parts. The first is similar to the test just discussed, and it involves averaging the test statistics for cointegration in the time series across cross sections, and for the other part, the averaging is done in pieces so that the limiting distributions are based on limits of piecewise numerator and denominator terms. The first set of statistics include a form of the average of the Phillips and Olliaris statistics. Zp tilde is equal to summation I from 1 to capital N into summation t is equal to 1 to capital T brackets EIT minus 1 hat, change in EIT hat minus lambda I hat brackets close, divided by summation t from 1 to capital T EIT minus 1 hat square, where EIT hat is estimated form. YIT is equal to x dash IT beta plus z dash IT gamma plus EIT, and lambda I hat is equal to half into sigma I square hat minus SI square hat, for which sigma I square and SI square are individual long run and contemporaneous variants of residual EIT. For his second set of statistics, Pedroni defines 4 panel variance ratio statistics. Summary. To summarize, unit root testing has the same significance in panel data as it has when the data is only time series. In case of panel data, some of the tests that are used to check the stationarity of the series are Levin Lin and Chu test, Pesaran and Shin test, Breitung's test, combining the p-value test and the residual-based LM test. Major tests for cointegration are Cow test, Pedroni test, and LM test based on the residual.